Oh, hell yeah. I love computers. A lot of people, especially cell phone people, will consider this a waste of time to screw around with computers and emulation, but it isn't. It's a lot of fun. When I first got online, I first used it to search ghost pictures and, you know, subliminal messages and aliens and, you know, backwards masking, like secret messages when you play an album backwards or something. And I used to be really superstitious, but I don't use computers for that crap anymore because it's fucking fake. I like to use computers to learn now. So I do shit like the video I just made about Starry Night Pro. I made that in a different emulator using Windows 98, but now we're using VirtualBox rather than 86box, and we're using Windows XP. Let's type it in. WinVer. Yep, Windows XP. Service Pack 3. So we can open up Starry Night Pro here, and it looks pretty nice, but it's pretty zoomed in, so everything's really large. But what's cool about VirtualBox is that you can go full screen, and you can go like this. Oh, now you got widescreen, old 2001 software. Where's the... Okay. What's kind of neat about this, though, let me go back to this view. You can go to Go, Companion Book, and then you can go to all these different events in astronomy. Like this one, Sun Eclipse 1. Wait, let me rewind it. Okay, so I'm going to go to seconds, and I'm going to hit play. And you'll see that it's just kind of a partial eclipse. It's like a little event that happened. And I can zoom in with the plus. I can zoom out. It's not a fully total eclipse, it's a partial eclipse. So let's go back to Go, and go to Companion Book, and then we'll go to the second eclipse. Alright, this one's kind of weird looking. Check this out. I'm going to go like this, and I'm going to hit play. Oops, shit. It's too fast. Alright, this crap is going way too fast. Seconds. Okay. Look, it looks like, if you look closely, it looks like the moon loops back on itself. Look at that. But that's actually not what happened. Look at the date. July 11th, 1991. This was a real eclipse, total eclipse event, and they could see it from, if you go to location, it's down in Brazil, you see that? It shows those location is circled there. So this was a real event, this really happened, but when you watch this, it looks like the moon loops back on itself, but it actually doesn't. It's just because it's almost like straight above, it seems like. Now I'll prove that. I'll rewind it, and I'll set the... oh man, that's beautiful, dude. Alright, so there... Okay, there it goes. I'm gonna go to seconds. Alright, here we go. I'm gonna leave it alone now. So I got the 180 fisheye lens. 180 degree fisheye lens. Look at that. Wait. That's... Man, that's awesome. I'm gonna do 180 again. Yeah, it's like basically right above you. So you can, while you're watching this, you can look somewhere else. You don't have to look directly at it. You can kind of watch the stars come out for a short time. It's crazy. Alright, let's see what the other events were. Okay, that's a partial. That sucks. I don't like partial eclipse. Partial eclipse to me is like useless. The real fun is the total eclipse. Yeah. Alright, let's go to the last one here for eclipses. Now what's cool about this view, look at this view. This view's insane. This is looking at the Earth, and you can see the outline of the moon on the surface of the Earth. And that little black spot in the center is called the path of totality. In order to see the sun be entirely eclipsed, you have to be within this little black spot. I think it's like 200 to 300 miles in width. So if you really want to see an eclipse, I don't know when the next one's coming up, you want to be in that path of totality. Very important. That's why I said I drove down to Missouri in 2024 to be in this spot. And it was worth it. It was definitely worth the drive. In fact, I couldn't even sleep when I drove down there, man. I I couldn't sleep because we didn't actually rent a hotel or anything. We just kind of went down there. We were expecting to sleep in the car for one night and then watch it and then get the hell out of there without having to pay for a hotel, right? But my dumbass, I thought that I could actually fall asleep in a car, and I couldn't. I guess I'm too picky or something. But, you know, we drove a few different places, Walmart parking lot, some random park somewhere in Poplar Bluff, Missouri. I just could not sleep in the car. I had my big 10mm gun with me, so it wasn't like that was an issue. You know, I had protection, but I don't know what it was. And then I made a video around that time. We went and stopped at this hospital. We were gonna sleep in the hospital parking lot, and then the craziest fucking thing happened to us. My dumbass didn't realize where the hell I was parking, and about 15 minutes after we had our windows rolled down, we had these screen protectors for our windows so no bugs would get in, and we can have fresh air coming in. We were trying to sleep in the back of my car. Had the seats down, so it was nice and comfy and everything, but I was just about to fall asleep, and you hear this in the background. Fucking helicopter right in front of my nose. I fucking stupidly parked right on a helicopter pad, essentially. I didn't even realize that was a helicopter pad right there. And this fucking helicopter, big bright light, loud ass chopper, woke us up. We couldn't fucking sleep. They were like airlifting somebody in or something, or out or whatever, but oh my god, that was the worst. So I couldn't sleep. I ended up staying up and waited till like 1:50 the next day, and that's, you know, I was able to pull that off. And so right when it was over, I started driving heading home, and I immediately started calling hotels, and I found one. So on the way there, about an hour drive, found a nice hotel and just crashed. Oh man, I'm not really good with the planning and shit, I guess, you know. I didn't expect I needed a hotel, but apparently, you know, I don't have an RV, so I couldn't sleep in my car. It's not comfortable enough. So this is pretty awesome. All right, so I wanted to try something else. Let's see. Oh, by the way, I'm gonna link voice chat if anybody wants to get on. I've been wanting people to come at me. My friend keeps hanging out there. I don't know what the fuck he's doing. So I'm gonna have to change my fucking room or ban his IP or something. Actually, I'm gonna have to ban his IP, dude. Cause, you know, I'm trying to fucking open up my chat and he's just sitting there all the time. I don't understand what he's doing. Let's see. Ah, fuck it. I'm not gonna worry about that right now. I'll just link this instead. Okay. So I'm gonna link one-click voice chat. Or Discord, nirvgorilla. Alright. So let me hit new. Oh shit, it opens up a new program when I do that. So here's what I'm gonna do. I'm gonna full screen this. I'm gonna go like this. And then I'm gonna go find let me turn the lights off. Let me teleport over to Jupiter. I'm gonna go to Jupiter. Alright, we're heading through space and boom, we're on Jupiter's surface. You see that shit? Now, we could see what it's like to see from Jupiter. And let's point at Earth. Okay, there's Earth over there. And let me just hit like fast forward and see what that looks like. If we just watch from, oh shit, that's too fast. Damn. That's also kind of fast. Okay, let me zoom in on Earth. I think you can get rid... Okay, cool. I got rid of the surface of Jupiter so I can see the full sky. So I can see Earth from Jupiter. Oh, you can zoom in quite a bit. Wow. Pretty good zoom ability. So you could see where the hell this is. And you can see other objects floating around. Oh, that's in the background. So where is the sun? Oh, there it is. It's off in... That's awesome, dude. Okay, let me go a little bit faster. Actually, I want to center and lock on this, but I also want to keep the Earth lit up. Now let me go to fast forward. I don't like how it's moving. Okay, I want to take this shit off. So, like with the Earth, you can go to info window, Look, and you get the night. God, it's just so cool, dude. The information is just so rich. Okay, I want to go further out. Let's see. Let's go to fucking Pluto. Fuck it. We're going way out to Pluto now. Holy fuck, that's far. Alright, I want to focus back on Earth. Okay. And I'm going to hit fast forward. And I'm going to zoom in. And that's a pretty different view of Earth, isn't it? That's the pale blue dot. Can we zoom enough? Oh, we can zoom in far enough to see where the moon is. Oh, that's cool, dude. That is so awesome, man. That's awesome. Holy fuck, the moon. I thought it was a little bit more. Oh, shit. Look at that shit, dude. This is where we at. This is our circumstance in space. This is where we are. We're here. That's home. That's here. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, live there, on the mote of dust. So that's Earth. Where else can we get to? Asteroids. Okay. How about we go this one? I don't know where the fuck this is, but let's go out there, wherever the fuck that is. Holy shit, that looks really far. Let's focus on the Earth, and well, that's not too far, I don't think. No, that seems pretty close, actually. That's an asteroid. So I want to go out even further than this if I can. Let's see. Go solar neighborhood. Holy fuck. Okay, let's go to Vega. All right, sweet. I'm gonna right click. I'm gonna go to Vega. Oh shit, there we go. Alright, now how do I get my screen back to what it was? I don't know if I can. View from center. I don't know what the hell's going on. Holy shit. I don't know what the hell's going on. Oh, that's actually really far away. As you can see, that's Earth going around our star. I want to go to Vega. Can I type in something? Let me go home. Okay. Where the fuck? Holy shit. I think it's kind of fucked. Let me go to new. I'm going to close that other one. Okay. Now, can I just type in? I'm not really used to this yet, so I want to see if I could just, like, type in. Find. Okay. Vega. Okay. I'm gonna hit go there. Wait a minute. Go there. Center. Selection. I can't go there? Get info. Information for the star Vega. Go there. There it is. Okay. Alright. What, I can't go on the surface or something, or what? So let's go to planets, and let's look back at Earth, and let's Holy fuck, that's so far away that I can barely even see Earth moving. Let me see, speed it up a little bit. Yeah, look at that. Oh my god. You can kind of see Earth going around. Look at that. It's so tiny. And there's the sun. There's Venus. There's Mercury popping up in and out. But because of the glare of the sun, Mercury kind of disappears, huh? God, that's so far away, man. But you can actually, like I said, this software allows you to kind of see from different perspectives. There's Jupiter up there. Pretty fucking far away. God, it's so awesome, man. That's so fucking awesome. What the hell's this? Saturn. Oh, you can, if you zoom out here, let me see. Okay, you can show the galaxy. Messier, okay. Stars. You can turn them on and off, turn planets on and off. Comets on and off. Constellations on and off. Equator. Okay. There's the outline of the Milky Way galaxy. Cool. Alright, so let's see what else. Satellites. That's at this time, this is 2001, so I don't think this really counts anymore. You can see it. Oh, there's the International Space Station right there. Oh, so wait, can you actually see where it is right now? So it is the 13th today. So at 12:47. I don't know if that's accurate, but if that's accurate, that's where the ISS would be. Okay. Alright, what else we got? Why is it so fast, dude? Ah! Okay. Solar neighborhood. Here we go. Holy shit, that's fast. Alright, so I'm gonna go to companion book again. Coordinate system, intersection. I don't know what the hell this is. Let's do 180 degrees. Oh, it's like stuck on something. Oh! I saw... Oh, shit. Okay, I don't know what the fuck's going on here. Companion book, rotation, day. Oh, shit, that's really fast. NCP. Polaris. Oh, that's like right... That's the North Star. What's the button to go there, man? I'm gonna go to Polaris. Shoom. Okay. Whoa, whoa, we're traveling through space. That's crazy, man. Look at that. Holy fuck, man. God, this software is awesome, dude. This is 2001 and it's fucking beautiful. I don't even know of anything that really... like is like up to par with this even. I mean, I could be totally, you know, blowing it, but I don't use a lot of astronomy software all the time, but I really don't know what else. I mean, I know there's online shit, but it doesn't even seem as good as this. So I'm zooming in back on Earth from wherever the fuck I am. Polaris, yeah, I think Polaris. Okay. I can't get any closer than this. So this is about, yeah, this is how far Polaris is away. Alright, let me see what else we got. Equator. Okay. Revolution. Alright. So yeah, let me alt tab out of this really quick. Oh shit. So you can also, like, instead of just looking at this stuff, you can go to my audiobook server and type in astronomy. Instead of just listening to music, you can actually learn about astronomy while you're looking at astronomy directly. So let me type in astronomy again. This is my audiobook server, and I think it's great having all these books. Where is my guy? Where's my guy? There he is. There's my guy. I love this dude. This is a professor, man. His name is Professor James B. Kaler, and he knows what he's talking about. So I'm just going to play.
Welcome to The Modern Scholar, where great professors teach you. My name is George Wilson, and I'll be your host. Today we begin a course entitled Astronomy, Earth, Sky, and Planets. Your professor is James B. Kaler of the University of Illinois. Professor Kaler received his B.A. in astronomy from the University of Michigan and his Ph.D. from UCLA. He has taught at Illinois for over 40 years. His research area, in which he has published over 120 papers, involves dying stars. But Professor Kaler's interests reach far beyond this topic, and he has published widely in the area of popular astronomy. Among his many critically acclaimed books are Stars and Their Spectra, The Little Book of Stars, The Ever-Changing Sky,
Venus
The 100 Greatest Stars, and Extreme Stars.
So when they call it like a transition, that's when like a planet goes in front of the sun. It doesn't really affect the brightness to the naked eye, but to our instruments, you can see the brightness go down when a small little planet transitions in front of the sun.
Which was the American Association of Publishers' choice for Outstanding and Scholarly Title in Physics and Astronomy for 2001. Professor Kaler also served as a consultant for the Time Life Books' Voyage Through the Universe series, and he appears frequently on various radio and television programs to discuss topics in astronomy. Currently, Professor Kaler serves on the board of directors of the Astronomical Society of the Pacific, and as one of the world's greatest living astronomers, he continues to be a much sought-after speaker.
Shit.
For almost as long as human history is recorded, man has looked to the heavens with wonder and amazement.
Wow.
Indeed, astronomy is among the most accessible of all sciences, for at a primal level, all one needs to do is look up. In the daytime, there is the sun, our closest star. Sometimes we see the moon, while at night we can feast our eyes on planets and myriad stars, not to mention the occasional interloping meteor or comet. But beyond this basic level, a world of fascination exists as we explore how over the centuries mankind has come to a better understanding of his place in the universe by gazing at the heavens.
That's beautiful,
and that
man.
is what this course is all about.
Holy shit.
Not just the natures of astronomical sights, but how they all fit together, how they were created, how they affect us back here on Earth, and what their fates, and perhaps ours, are likely to be. For more information on this lecture, please visit the course's webpage at www.modernscholar.com, where you'll have access to links to related sites, a seminar room to share your thoughts with other students, and, yes, of course, a final exam. And now we begin astronomy, Earth, Sky, and the Planets. And now, Professor Kaler. Astronomy,
Big Dipper.
Earth, Sky, and the Planets. Lecture 1, We and the Universe.
I'd like to welcome you to the first
Dipper.
of 14 lectures in this course on the astronomy of the solar system. We will look at everything from the sun out to the most distant reaches of the planetary system and beyond, going almost halfway to the nearest star. The lectures here are going to cover the motions of the Earth around the sun, the spin of the Earth and the effect that it has for those of us upon it. We're going to look at the physical natures of the planets. Why is Mercury different from Pluto? Where is it? Why is Jupiter different from the Earth? We're going to look at all the planets of the solar system. We're going to look at the debris of the solar system. We're going to look at how this whole system was put together. In this first lecture, however, we're going to look at the big picture. not just the planetary system, which is going to be introduced, but at the grand scheme of things, where we look not just at the sun and at our local area, but we look at the stars around us, we look at how these fit into the entire galaxy, we look at how the galaxy fits into the universe at large, and most important, get some idea of the scale of things.
Jeez.
I like to think that I've been an astronomer for over 50 years, since the time I was 8 years old, when I first got interested in this subject. I got interested really because of the beauty of the nighttime sky. I was walking with my grandma, and I said, "Stars have points, don't they?" And she said, "No, they don't have points. Look up and take a look." And I looked up. Sure enough, there's a star up there. It's kind of orange in color, and it didn't have points. It was kind of roundish and sparkly, and that orange color just fascinated me. And I kept looking at it, and a year later, there it was again, and I looked at it again, and I was gone. I knew at that point that all I wanted to be in life as a professional was an astronomer. It goes to many things that are very personal to me. It goes to the beauty of the nighttime and the daytime sky. The daytime sky the astronomer is equally at home in the daytime sky. We have the sun, we have the moon, we have the blueness of the sky. We have all manner of phenomena that we can see. In the daytime, we can see the Earth in the daytime, which of course is an astronomical body as well. Why do we want to study astronomy? For a variety of reasons. Astronomy is a very good example of how a science works. It's exemplary of all sciences, for that matter. But it's the science, in a sense, of everything. We study not just the planets. We study not just the stars. We study the universe as a whole. And to understand the universe as a whole, we have to understand the very small, going down to the very atoms that make us. We are looking outward from an astronomical body. We are one planet of many in our planetary system. Maybe one planet of hundreds, maybe millions in our galaxy. We still do not know. We need to understand our own Earth. We can't experiment on our Earth. We would like to understand our Earth better. How do we do that? We understand our Earth better by looking at the other planets and getting some idea of what they're like and why they are as they are, and feeding that information back to understand our own precious planet. The stars have a great deal to do with us. We live because of sunlight upon the Earth. We live because the sun is a stable star that will shine for billions of years into the future. Not only that, the sun reaches out to touch us with its matter, with a wind that it blows, that hits us, forms the northern lights, perhaps deposits more energy into the Earth. We came from out there. All of what is out there fed back into us. We came from out there because of the accumulation of material from the galaxy that wound up forming our sun and forming our planets. We are children of the galaxy. We are not isolated. If we are to understand our Earth at all, we have to understand our environment. And that means not just near space, the inner part of the Earth. It means understanding the moon, and it means understanding the planets and the origin of all of this system. And that is what this course is really all about. Let me tell you a little about what we're going to do over the course of these 14 lectures. We're going to start with the Earth, with the rotating Earth, with the Earth going around the sun, so we can get some idea of how things appear to move in the sky, why the stars rise in the east and set in the west, why the sun appears to move against the background of the stars, why the seasons exist. We're going to look at inner space. We're going to look at the atoms that construct everything. We're going to look at the light that allows us to learn something about the natures, the compositions, and even the origins of the planets that are out there. We're going to begin to look at the physical natures of the planets, from the Earth through the moon, beginning and sweeping through the planetary system from Mercury on out all the way to the distant planet Pluto. And then begin to look at the debris of the system, and finally at the end in Lecture 14 put it all together and see how it was all made. And see how our Earth was created and why our Earth is so special within this marvelous planetary system. So let's take a look at the planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Most school kids learn these things in order. And that sort of gives you the idea that all the planets are the same, that they're all alike, and they aren't. They're all natural experiments. And by looking at the other planets, we can tell something about ourselves. They are all formed under different conditions and different distances from the sun, different sizes, different masses. In an experimental science, you go into the lab, you change, you tweak the input, see what happens to the output. We can't do that to the Earth. We don't want to do that to the Earth. But nature's given us several other experiments that we can use. We can see what happens to Mercury. Why is Mercury the way it is? Why is Pluto the way it is? What conditions have changed them? And that leads us back once more into understanding ourselves. So look at the planets now in order outward from the sun in a little bit more detail. We'll keep increasing the detail until we begin to understand them better and better. Mercury, Venus, Earth, Mars. They're all rather similar. They're all made out of rock and metal. They're unusual bodies. We know of no other bodies in the universe quite like ours. There's a strong feeling of people who begin to learn astronomy that we are insignificant on this little rock way out on the edge of an anonymous galaxy. And one of the other themes of this course is that is simply not true. We're in a very special place on a very special body, a very unusual one that is unlike anything else that we know anywhere. Mercury, Venus, Earth, and Mars, the terrestrial planets, after Terra, ourselves, we're all similar, yet we're all different, we're all individuals, and I don't mind throwing the moon into that as well, making 5 terrestrial planets. If you were walking on the moon, you would feel very much like you're walking on the Earth. A little lighter, you'd bounce around a little bit more because the body is less massive than we are. But if it looks like a planet and it feels like a planet, as they said about the duck, if it quacks like the duck, it's probably a duck, and that's what we have here. If it looks like a planet, it's probably a planet. So let's count the moon in on that as well. So now we've got 5 in the inner part of the planetary system. And then you look out farther, and you see these 2 giants, Jupiter and Saturn, enormous bodies that are terribly similar to each other. Jupiter, Saturn, Uranus, and Neptune are often put together as the Jovian planets. That's really not quite true. Jupiter and Saturn are very similar to each other. What we say about one, you can pretty much rely on being true about the other. Giant bodies, 10 or more times the size of the Earth in dimension. And then you move out farther to Uranus and Neptune, and they're smaller. They're very different from Jupiter and Saturn. They're rather unusual bodies in their own right. We don't understand them very well. In fact, we understand things less and less, really, the farther away we get. So now we've got 3 kinds of planets. We've got the 5 in the inner solar system, and we've got the 2 giants a little farther out, and then we've got Uranus and Neptune, which are farther out yet. And then there's little Pluto, about which everybody argues. Is it a planet? Is it not a planet? It's one of the most common questions I get from people. Is it a planet? People seem to be very concerned about the fact, well, in some ways it is, yes, and you can, some ways, maybe we should exclude it. I kind of like to include it. So now we've got 10 planets. If we threw it out and we threw that the moon, we'd have 8. You see what I mean? There's no strict definition, and that gives us a lot more freedom. And then we can take the little bodies in between Mars and Jupiter that everybody's heard about or maybe read about in science fiction stories, the asteroids. And we could collect them all together. We could call them a planet too if we really wanted to, and that gives us 11. So the definition is free and floating, and I'll continue to use it, free and floating. Remember when you were in first grade, maybe 4th grade, elementary school, and the teacher in your classroom had this panel up on the wall of the planets. This huge sun and the big planets all in a line outward from the sun. I hate to tell you this, but they lied. It's not true. It's not the way they look. We have to deal with scale in this business. And it's important at the outset that we try to set the sizes of these planets in the context of the distances between them. Because almost everything is empty space, or at least filled with, even if it's empty, nothing is truly empty, of course. But the separations between things in astronomy are enormous compared to their sizes. A truly, truly underappreciated fact that is rendered a falsehood by the cartoon images that you generally see in classrooms. And sometimes we really have no choice because it would be impossible actually to draw a scale model of the solar system in a classroom. By the time you make the sun big enough to see, or the separations big enough, the Earth is so small you'd need a microscope to see it. So let's really start this particular lecture off after this introductory material by trying to put things into some kind of scale and into some kind of context. The sun is by far the biggest body in the whole planetary system, in the whole solar system. It is called the solar system for a reason. The planets are the satellites of the sun. They're the moons of the sun. The sun dominates everything. 1,000 times more matter in it than all of the rest of the planetary system put together. It's almost 1 million miles across, 1.5 million kilometers across. Its mass is 300,000 times that of the Earth. It's 1,000 times more massive than the largest of the planets, Jupiter. We're separated from the sun by about 100 solar diameters. The distance between us and the sun is a standard unit, which I'm going to refer to a lot, and I'll try to remind you of it off and on as we proceed through the course. Standard unit called the astronomical unit, with a capital A and a capital U, the AU. It's 93 million miles. It's the average distance between the Earth and the sun. Average, yes, the distance between the Earth and the sun does change a little bit. It has no effect on us at all, no effect on the seasons, as you'll see later, but it is a minor change by a few percent. So we use the average and call that the astronomical unit. 93 million miles, almost exactly 150 million kilometers. And then we scale everything else to the astronomical unit. It's the fundamental distance unit that is used in all of astronomy, not just from the planetary system, but ultimately through distances to the stars, distances to the most distant galaxies. The distances out, and we can get pretty boring just listing off statistics, so we'll try not to do that too terribly much. Mercury is 4/10 of an AU out. Venus is 7/10 of an AU out. So we're kind of nice and symmetrical. 0.4, 0.7, and then us at 1.0, and then Mars out at around 1.5. And close into us, the Earth is something of a double planet, really. We have the Earth and the Moon is 250,000 miles away. We won't even deal with that in terms of the astronomical unit. It's very close. And it's kind of interesting to think when we look at all these distances, and we are so proud of ourselves for getting from here to the Moon. That's all we've gotten, 250,000 miles. That's it. The sun is almost 100 million miles away. The Earth is, as large as it seems to a human being, is a terribly small body. 8,000 miles wide, 13,000 kilometers wide. It's only 1/100th the size of the sun. The sun is 109 times, actually, if you want the real numbers, 109 times the diameter of the Earth. The sun is 1/100th of an astronomical unit across. That makes the Earth 1/10,000th of an astronomical unit across. If you had the Earth a marble, say a 1 centimeter marble about this big, the sun would be a wagon wheel about a football field away. And you'd see it off there in the great distance. Let's use this scale for a little while, and we'll start looking at where the other planets are, because where Pluto is, you couldn't even see to it. It would be so distant, even on this scale. And eventually we'll have to shrink down the scale to even begin to put the galaxy on, our home, our collection of stars. From here on out, we go to Mars at 1.5 astronomical units. And then we make a tremendous jump to Jupiter. It's 5 astronomical units away, 5 times farther than we are from the sun. And on our Earth is a scale of about this big. Jupiter would be about the size of a, good-sized softball, perhaps a little bit larger. Located, this is 500 million miles from the sun, 5 astronomical units away. That's 5 football fields away, if you like, on this scale. And then we make a tremendous jump out to 10 astronomical units to see Saturn. And then we make a farther jump out. We almost double it again to 19 to get to Uranus. We just keep going farther and farther away. Now we're taking ourselves all the way out to Neptune, which is 30 astronomical units away, which some people think is the sort of the end of the planetary system, because, again, Pluto's...
So we're at Halley's Comet right now, I believe, and we're looking in the very distance. That's the sun. There's Venus over there. Wow, that's fucking far away, dude. Let me target Earth again. So from Halley's Comet, I'm going to see what Earth looks like. Oh my God, that's awesome.
Sometimes it's included, sometimes it isn't. It's a curious, strange transition body that is eventually going to tell us a great deal about the planetary system if we can ever get to it. It's the only planet we have not yet visited by spacecraft. We will eventually. It's a long, long journey. It takes about 10 years for a spacecraft to get out there from here. Moving even fast enough to break free of the gravitational field of the Earth and the gravitational field of the Sun, so it can float forever out there, moving off into the galaxy. Pluto averages 40 astronomical units away. Now, there's a lot of consistency in these planets. They all go around the Sun in pretty circular orbits. The Earth, quite circular. There are a couple that are a little bit off center, Mercury and Mars, but not terribly much. Pluto is way off center. It goes from the orbit of Neptune all the way to 50 astronomical units out. One of the things that we thought makes it not quite in the same category as the rest of the planets. It's also a highly tilted orbit. It takes us out to the outer fringe of the planetary system where we find an enormous number of icy bodies that are called comets. There's a lot of misconception in this business, and people are constantly confusing comets with meteors. A meteor is a small rock, actually a little asteroid for the most part, or a little piece of comet fluff, as we'll see, that hits the Earth's atmosphere and goes streaking across the sky. Comets do not go streaking across the sky. They're orbiting bodies that orbit the sun on long, skinny orbits that take them way out to the outer part of the planetary system and then close to the sun. They're made mostly out of ice. We have found and can see now a huge reservoir of these cometary bodies out beyond the orbit of Pluto. In fact, many of them share the orbit of Pluto, which means that we could put Pluto out there in this band of icy bodies, which actually has a name. It's called the Kuiper Belt, after Gerard Kuiper, an astronomer of the mid-20th century who first postulated it. A few of these things work their way in. They're ice balls that get heated up by the sun. Sunlight, then the pressure of sunlight, the pressure of the wind from the sun is blowing a wind from its surface, pushes the gas and the released dust and dirt particles in the comet away, and you see this long streaming tail that very slowly works its way around the sun, visible night to night, very much as the planets are. So now we've expanded the planetary system into the region of the comets, out beyond Pluto. And it turns out that Pluto is one of them. It's not a comet. Don't get confused on that. It's not a comet. It's a transition body. It's a body that, in a sense, tried to be a planet, but because of lack of raw material, couldn't quite make it. And then we've got another huge reservoir that takes us almost halfway to the nearest star surrounding the sun. It's called the Oort cloud, O-O-R-T, after Jan Oort.
So if I fast forward long enough, eventually... Oh shit, there we go! Holy fuck, dude! It's true! Look at that! We're getting closer to Earth. We're slowly getting more closer to Earth on the body that we hitched a ride from. I saw the Earth fucking slowly getting closer. Oh man, we're getting pulled into the solar system, dude. On Halley's Comet. Oh my god, there it goes. Oh shit. Holy fuck, man. That's crazy. Oh my god, dude. That's fucking awesome. We're getting further away, you can tell. Dude. So what year was that? Because that's when Halley's Comet is going to be close to Earth again. So let me target back on Earth and see when this was about. So sometime in 2062. Yep. 2062. Look at the date down there. And if I do a Google search, 2062 Halley's Comet. Let's see if appearance dates. Oh, predicted to return in mid-2061. See? This software is fucking awesome, I'm telling you. It's fucking awesome.
Astronomer of the mid-20th century who postulated that one too. And that's a reservoir of very long period comets that were created in the planetary system eons ago, were tossed out, but still belong to the solar system. So the solar system is vastly larger in scale than the planetary system. So now we've got the planets. Well, you can count Pluto, you can count the moon. Doesn't matter. We know what they are. It's what they are that counts, not exactly what you call them and categorize them. And we've got this band of comets outside the orbit of Pluto and this huge reservoir of comets around the sun. And then we got a whole bunch of little bodies in between Mars and Jupiter called the asteroids. The biggest one is not terribly large. It's considerably smaller than the moon. You roll them all together, you might have gotten an Earth or something like a terrestrial planet. It's kind of fair to call them a terrestrial planet collectively, and if you were walking on one, the biggest one, certainly named Sirius, certainly feel like you were, except you'd be a lot lighter. So we now have at least something of an inventory here of the planetary system, and we will, over the course of this course, over this set of lectures, be looking at all of them in fine detail, beginning with the Earth in the middle, looking outward into the sky at the context of the orbits of the planets around the sun, how they move, and then in detail about their physical natures, and eventually where they all came from. And eventually, where they're all going to go, too, because nothing is permanent. Everything is born and everything dies. And part of astronomy is learning how things are born and how things die, where we came from and where we're going to go. But we have to put the solar system and the planetary system make no sense if you can't put it into a broader context. The sun is a star. Now, generally, the common phraseology is to talk about the sun and the stars. And when we talk about stars particularly, you're talking about all the other ones out there. But keep in mind always that the sun is just one of their number. You go outside on a nice clear night out in the country with no moon. The average human eye can see maybe 2,000, 2,500 stars. Over the course of the entire sky, the entire night, if you go around the globe, there are probably around 8,000 that are visible to the human eye, depending upon how old you are and what your level of light pollution is. This is just the beginning. They all look pretty much the same when you stand outside at night and look at them. They just appear as little points of light, but look carefully. Look very carefully, and you see colors. There's some that are a little reddish. There's some that are kind of orange. Even some take on a little bit of a blue tint that reflect their temperatures. The blue star's hot, the red star's cool. The sun is often considered as kind of a yellow-white star. It has that kind of cast to it. And temperature of about 6,000 degrees Kelvin. I hate to introduce a new temperature scale to you because in this country, in the United States, we have...
If you haven't seen it, the Hubble Ultra Deep Field is where they zoomed in on a small part of the sky, like here, for instance. In a small little box, they focused for, what was it, I think 11 days or something? So the Hubble took a picture after zooming in for I don't remember how many, I think it was 11 days. And they just saw tons of galaxies. This is a real picture. And of course, every galaxy has billions of stars. Each one of these little points of light, billions of stars. We're in the middle of fucking nowhere, surrounded by billions of stars, billions of galaxies, and there's no hint that help is going to come from elsewhere to save us from ourselves.
To deal with Fahrenheit and Celsius or centigrade. And in Europe and Canada and the rest, people stick with centigrade. It's a pretty simple system. Centigrade, it goes from 0 at freezing, water 100 at boiling. But then you go down and down and down to negatives until you get down to a point that's called absolute zero. It's minus 273 degrees centigrade. So we just start at 0 and work our way up. That's all. In centigrade units. And the sun in that scale is about 6,000 centigrade degrees above absolute zero. It puts things in sort of a context for you. Stars range in temperature from not much hotter than that of a self-cleaning oven, believe it or not, about 1,000 degrees or cooler. So cool you can't even see them with the human eye, to a maximum of close to 1 million. It's a spectacular range. In dimension, there are stars about the size of Manhattan. And there are stars the size of the orbit of Saturn. Another spectacular range. Stars, little light things, perhaps not much bigger than Jupiter in mass. If you want to stretch the definition of a star, which it really requires, you see at some point we have difficulty in even defining what a star is sometimes. I like to define it as a body that at some point in its career goes through this nuclear fusion process. And you have stars that are 100 times as massive as the sun. The sun, we know, is going to die out as a little body the size of the Earth sometime over the next several billion years. You go to stars that are much more massive than the sun, they blow up, they explode. The sun can't do that. One of the nice things that we have learned, the sun cannot explode. But some of them do. And the ripples of the exploding stars spread throughout the universe, help create new stars. They provide the chemical elements that created us. That's getting a little bit ahead of the story, however. Let's look back at the stars and a little bit at the scale. The nearest star, as close as it looks, this star called Alpha Centauri. And here you get into another argument, because Alpha Centauri is a triple star.
That's what I want to look up.
Two of them go around and orbit about every 80 years, very close together. The brighter, very much like the sun. Rather curious, an interesting coincidence. And then there's a little one a little bit farther away, a couple of, maybe 10,000 astronomical units away from the double, which is called Proxima Centauri, and that's a little bit closer to us. But Let's not quibble about this. Call it Alpha Centauri. How far away is it? It gets difficult to use astronomical units at this point. The star is about 270,000 astronomical units away. We need a new scale. You want to match your distance scale to the things being measured. Otherwise, you wind up with little bitty numbers or you wind up with enormous numbers. So let's introduce the light year. And we'll scale it back to the astronomical unit in a minute. The light year is the distance, not a unit of time. It's commonly taken as a unit of time. No, it's a unit of distance. It's the distance a ray of light will travel in 1 year. Oh, is that hard to appreciate? Light moves at a speed of 186,000 miles per second, 300,000 kilometers
7
per
times
second.
around
That's
the
8
Earth.
times around the Earth, 1 second. Here to the moon in a second and a half. From the sun to here in 8 minutes. We could say the sun is 8 light minutes away. Pluto is several light hours away. Interesting aside, if you visited Pluto and you want to talk to the folks back home, you start talking and your telephone message doesn't reach back home for another 4 hours. Long way to go. That is, we see things as they were in the past. You do not see the sun as it is now. You see it as it was 8 minutes ago. The nearest star is 4 light years away. It's about 270,000 astronomical units. So the light year and other units similar to that become the standard for interstellar use and even for use across the whole universe, for that matter. One of the more common questions that I will get is, doesn't that bother you? You're looking at stars. The nearest star is 4 light years away. You're seeing as it was 4 years ago. What's it doing now? It could blow up, which it can't. It can't. Relax, it can't. It could blow up, and you wouldn't know it for 4 years. And yes, that's absolutely right. And I don't care, because I can't know anything until light gets to me anyway. So my now is when the light gets to me. Now, if you want to walk around your house or your office in a daze, think about this. You're looking at your colleagues or at your family. Light travels about a foot in a trillionth of a second. You see everybody around you as they were a few trillionths of a second ago. You don't see them as they are now. And the people farther away from you, you see more farther into the past. So you're not looking at anything in that context, that sense of now. Now is when the light arrives. So none of this bothers us very much. We simply ignore the fact that there's a light travel time. We see things as they are when they get to us. And we're looking at all the stars in the sky at different distances, and we see them as they were in the distant past. All at different different stages in their ages. And that's really not a problem, because stars live for far longer than that little light travel time anyway. They live for millions and billions of years. Who cares about a few thousand here and there? Just like when you're looking at your colleagues, a few trillionths of a second in the lifetime of a human being doesn't mean anything at all. So it really matters not. And we can forget the whole thing, otherwise we wander around like this wondering, you're looking at everybody in the past. It can drive you crazy after a little while. So we forget about it. 4 light years, it's a long way to go. It's why we haven't gone to the stars and why it's going to be very, very difficult to go. The distances are spectacular. You can't even use this Earth as a marble scale. Let's take the sun as a marble now. We'll shrink it down from the wagon wheel down to the marble, and the Earth is about that big. It's about as big as a grain of sand on that scale. The nearest star is 170 miles, about 250 kilometers away. The scale is really to take small marbles and put them in the major cities of our country. Now start them rolling around, because stars move relative to each other. The sun moves about its own diameter in a day. So you have these marbles shifting a diameter in a day, and they're separated by 100 miles, 200 miles, maybe more. Do you think they're going to crash into each other? I don't think so. We're very safe out.
Isaac Newton believed that a single idea could explain why objects fall to the ground and why the moon goes around the Earth. The Earth exerts a downward force on objects, which causes them to speed up or accelerate when they fall. When an object is thrown horizontally, it experiences the same force and accelerates downward at the same rate as when it falls straight down. The faster the object is thrown, the farther it goes before hitting the ground. Newton imagined that if an object were launched with a very high speed, it would curve far around the surface of the Earth. With precisely the right velocity, an object would go into a circular orbit, continually falling toward the center of the Earth, but never getting any closer to the center. Still higher velocities would put the object into an elliptical orbit. Newton realized that the motion of falling objects, projectiles, and celestial bodies could all be understood by a single universal law of gravitation.
He was brilliant.
Scientists today use Newton's law to compute the trajectories of space probes, which must be accurate over millions of miles.
There's an apple on that thing. So he put an apple. So Newton is considered the greatest human who ever walked the planet. Like, he was plugged into the physics of the universe. Isaac Newton. He really lived. Ah, the orbit.
Our Earth is but one small part of a vast system of planets, satellites, asteroids, meteoroids, and comets that revolve around the Sun. 9 planets orbit the Sun and move in the same west to east direction. All of them, except the outermost, move in roughly the same plane. Mercury, then Venus, Earth, and Mars are small planets that are relatively close to the Sun. Jupiter, Saturn, Uranus, and Neptune are large gaseous planets. They probably contain little rock and iron, but are made up of hydrogen, helium, ammonia, and methane.
Why doesn't Wikipedia have
Pluto,
stuff like this?
the farthest from the Sun, appears to be somewhat terrestrial, but is so small and distant, astronomers know little about it. Pluto's orbit is inclined relative to the orbits of the other planets. While the Earth has only one moon, most planets have several moons or satellites orbiting them.
There's an important reason for that. Because those other planets out there, they pull in objects into the gravitational influence, and they become moons. But our moon cannot possibly do that because it's so big. It's 1/3 the size of Earth. So what actually happened, the moon, our moon, is a chunk of the Earth that broke off in its infancy.
Asteroids are small, irregularly shaped fragments of rock that are located mostly in a circular belt between the orbits of Mars and Jupiter. Meteoroids are small chunks thought to be the result of asteroid collisions.
What do you mean satanic? What are you, a retard? You're a
Comets
retard, dude.
have a solid nucleus surrounded by a head or coma of dust particles and frozen gas.
That's one of the schizophrenics I was talking about. They think Satan is real.
Comets have a solid nucleus surrounded by a head or coma of dust particles and frozen gases. The characteristic comet shape comes from a long tail of dust and gas driven away from the coma by light and particles from the sun.